Okay, my microphone is on. I'm recording. All right, so we're going to start chapter 3. So this is two-dimensional motion. So it would help if y'all had a handout. This is going to be very, very helpful for you to have. All right, so when I look at the motion of an object that is moving up or down, or both, and forward in one direction at the same time, I have to evaluate the motion a little bit differently, all right? So if I look at a ball that is rolling off of a horizontal desk, and I was to watch that motion, then what would we say is the motion of this ball?
Forward and down.
So it goes forward and down. And this ball never actually goes up. So this makes this kind of motion a little bit simpler than the second kind of motion. So that ball has an initial velocity that is to the right in this case. And then if I was to sketch the path, it's going to go forward and then down in a parabolic path. All right, so we have not talked about forces yet, but we've experienced one particular force all the time, and it's the force that is causing this ball to move down. So what is that? Gravity. And what direction does gravity pull? It always pulls down. So one thing that we have to note is that the only force acting on the ball is gravity. All right, so, and gravity is going to be pulling this ball down. All right, so that's something that we know. If gravity is the only force acting on the ball, and that ball is being pulled down by gravity, what can we then say about the motion as the ball is moving to the right? Is there anything that is pushing or pulling that ball to make it speed up or slow down as it rolls to the right? If I just think about just the left to rightward motion of the ball, what do you think?
So
Gravity is still acting on it, but what way is gravity pulling? Down. So when we look at the motion of a projectile is anything that is traveling through the air, that gravity is the only force acting on it. When we look at the motion from left to right, there is no force acting on it, pushing it or pulling it to the left or right. All right? So there are no forces to the left or right. So it moves with a constant velocity to the right. All right, so these are two fundamental concepts that we have to think about when we're talking about a projectile. So a projectile, most of the time in physics, is something that is moving forward and either up or down or both at the same time. All right? So because of that, we have to analyze the motion in the x and y directions separately. So So if I am looking at the direction that this ball travels, or the velocity of the ball to the right, I can say that this is the velocity, initial velocity in the x direction, because this is a ball that is rolled off of the desk, and its initial velocity is all horizontal. It's all to the right. I can also say that its initial velocity in the y direction is 0, because until it leaves the table, it is not moving up or down. It is not crashing through the surface of the table. It is not levitating above the table. So its initial velocity is only to the right, right? I also know that it has some acceleration in the y direction, and that is going to be equal to negative 9.8 meters per second squared. So my velocity in the x direction, however, is constant. So if I have constant velocity, what is my acceleration?
Zero.
It's 0. All right, so there's a couple of other measurements that I am going to keep up with here. So I am going to measure this distance here, and this is going to be what's called delta y. And delta y is going to be my drop height, just like we saw with the when we did the tennis ball and we dropped the tennis ball. That's going to be drop height, and so we're going to call that delta y. And then this distance here, I'm going to call delta x. And sometimes this is called the range. You'll see that term occasionally. The drop height is going to be a negative number because it is moving down. So this ball is going to have constant velocity to the right, but it's going to start with a velocity downward that starts at 0 and accelerates downward as it goes because of gravity. So there are going to be a couple of formulas that we're going to use. So we know that velocity in the x direction, if it's constant, then that's going to be delta x over t. So the formula that I'm going to use is just a rearranged version of this. And this is going to be one of the key formulas that I'm going to use with these problems. So when I go to find delta x, the distance that it travels forward, I need to know the initial velocity, which is all going to be in the x direction, and I need to know the time. But most often, you will not have the time. You'll need to calculate the time. And so we will typically know delta y. We will know the acceleration in the y direction, and we will know the initial velocity in the y direction. So we need to calculate time. So we're actually going to use a familiar kinematic equation. We're going to use delta y equals VI y times t plus
Thank you. Sorry, we were at the college today.
okay,
Should we grab a packet?
not that one, you need this one. And I'm recording class, so
Thank
you
you.
can, there's 2, I gave her 2.
Okay, thanks.
So you can go back and watch what you missed. Okay, so we're gonna use VI in the y direction times t plus 1/2 a in the y direction times t squared. All right, so this is the kinematic equation. We know, we're almost always going to know how high this cliff is or this desk is, so we know delta y. we're always going to know that since this rolled off the desk horizontally, that its initial velocity in the y direction equals 0. And we always know that the acceleration due to gravity is 9.8 meters per second squared in the downward direction. All right, so we are going to solve for t. Can I simplify this equation? So if I look at these things, so I'm going to be given delta y, I know a, and I know VIY. Can I simplify this at all?
Yes.
What can I simplify? Okay.
DIY is 0, you can just get rid of that.
Yep, VIY is 0, so I can get rid of this, and it makes my life a little bit easier. So I'm going to rearrange what's left. Delta y equals 1/2 a in the y direction times t squared, and I'm going to come up with t equals the square root of 2 times delta y over a. And this right here is going to be the second big equation that we're going to use. Oops, that should have been a fraction there. All right, so the sequence of events that we are going to follow is most of the time we are going to have to do this equation first because we don't know how much time it takes for this to drop. And then we're going to come and use that time in our second equation. Very typically, you're going to be asked, you're going to be given a problem that says a ball is rolled off of a desk that is 1.3 meters tall with an initial velocity of 2 meters per second. How long did it take to drop and how far did it go? So we're first going to solve for how long did it take before it hit the ground. And secondly, we're going to solve for how far did it go. All right, so important things to remember. Important things. VI, initial velocity, is the same thing as velocity in the x direction, and this is always going to be constant. All right, so our VIY will be 0, just like a ball dropped from rest. Then we're going to solve for time first using the motion in the y direction, and we're going to solve for delta x second using the time calculated in the first step. I would say the other really important thing to remember is analyze motion in the x and y directions separately. All right, we good? Okay. Now, let's look at our second scenario for projectile motion. So the second scenario for projectile motion is when we have something that is launched or kicked or thrown, and it is thrown upwards at an angle or downwards at an angle. It works the same way. We can kind of trace the path that this takes. It's still going to be a parabolic path, but things are going to be a little different. So if this is our initial velocity, we're going to have an angle theta. And we're going to have initial velocity in the y direction and initial velocity in the x direction. we're going to have the same delta x, which is still going to be the distance that it travels, and we're going to say this is delta y, which is the height that it reaches. But we also are going to know that the velocity in the y direction at the top of the path, in this case, is going to be 0. Just like a ball thrown upward. And the velocity in the x direction will still be constant. All right, important things to remember here. TBD. This is going to be a later lesson. We're going to come back and look at this next week. All right, turn the page and let's do a problem. A ball is rolled off a desk that is 1.2 meters high with a velocity of 2 meters per second. How long will it take to hit the ground, and how far away from the desk will it land? All right, so I've taught you guys the SKES method for solving problems. Well, now you have to have a sketch. All right, at this point, if you don't have a sketch for your work, it's going to be very hard for you to get things right. Now, the sketch and the givens are going to look a little different because most of the time your givens, let me switch back to black, are going to be written on the sketch. So this is VI is going to be 2 meters per second, and this is going to be the velocity in the x direction. It tells me that my desk is 1.2 meter high. And so that's going to be my drop height. But remember, this needs to be a negative number. So super important that we remember that the ball is moving downward, so delta y needs to be negative. I'll show you what happens if you forget. All right, we also know that acceleration in the y direction is going to be negative 9.8 meters per second squared. And if I kind of draw a little sketch of my path, then this is going to be my delta x. I can also say that my initial velocity in the y direction is going to be 0 because until it leaves the desk, it is not moving up or down at all in the y direction, so its initial velocity will always be 0. So what I'm going to do is first I'm going to solve for time using the variables in the y direction. Oops. So I'm going to say delta y is VI yt plus 1/2 at squared, and this is a in the y direction. VIy is 0, so I'm going to rearrange this. So time is going to be square root of 2 times delta y over a. So I'm going to put this in 2 times negative 1.2 meters divided by negative 9.8 meters per second squared. And what do we get when we solve for time here? Have you calculated that, Mark?
Yeah, 0.5 seconds.
0.5 seconds. I would say if you end up with a decimal, try to give me more than just 0.5. It's not that wrong for you to round this to 0.5, but probably a little bit more accurate for you to give me 2 decimals. All right, so it's going to take 0.49 is what I calculated seconds. Now I can use this time and I can plug it into the equation for delta x. So this is going to be Vx times t. And so this is 2 meters per second times 0.49 seconds. And so delta x is going to be 0.98 meters. So those are going to be the steps that you're going to follow for about 90% of the projectile motion in the horizontal direction problems that you're going to see. All right, there's going to be a few problems that you will see that are a little bit different, but you're using the exact same equations, and the variables are going to be the same and the concepts are going to be the same. All right, so I want you to do the next one, the cannonball. Yes?
Where did we get the second equation?
The second equation? So this one? So since my velocity in the x direction is constant, velocity is going to equal the change in distance over time. So there's no forces pushing or pulling it to the right or left. So if it's going this way, it's just going to keep going that way until something stops it. All right? So I just rearranged this equation to solve for delta x. Mm-hmm. So, Mark, if you're done, what I want you to do is I want you to practice and tell me what happens on your calculator if you forget that displacement, that delta y, is a negative number.
You get the square root of a negative number.
You get the square root of a negative number, what's your calculator going to tell you?
It's a non-real.
It's going to tell you error.
Error.
So you're going to end up with your calculator saying error, and that's just your calculator's way of saying, hey, I'm too stupid to figure out that you just forgot a negative sign.
Error, non-real.
So if you forget to put a negative here, then you're going to be trying to take the square root of a negative number, which you can't do, and your calculator is going to return an error. So if you see that, it's just real common as you're starting out with these problems. It's really common to make that mistake. So you're just going to go back and say, okay, I missed something somewhere. All right, so your homework tonight is to do the practice on the next page. All right, so over the weekend you have 2 problems to do, and that's it. So I'm going to give you a card, and it's going to have a height and initial velocity. And so Mark and Malachi, you guys are going to be partners. So I want you in the first problem to write down the height and the initial velocity that I give you. And then for the second problem, I want you to write your partner's numbers. And so you two are doing the same 2 problems. So then you can check your work against each other. And yeah, so it doesn't matter what order you do them, but Lily and Olivia, you're going to do those 2 problems. All right, so then for John and Gianna and Bella and Lydia, I am going to give you guys some numbers. So, John and Bella, you're going to do 36 meters and 16 meters per second, and 21 meters, 2 meters per second, and then Gianna and Lydia, you're gonna do 23 meters and 4 meters per second, and 32 meters and 10 meters per second. Okay, thanks. So that is your only homework for me over the weekend, is just to do those 2 problems. So you have only 1 minute till